Hello everyone and welcome to today's lecture. Today we're going to be talking about the concept of set theory and how to define and learn about what exactly a set is and how they interact with one another. So set theory is an axiomatic system that properly defines a mathematical set or mathematical sets and how such set interact with one another. And in some sense, there are two different ways of going about learning set theory. An easier way and a slightly more difficult route. And the easier way is what's called naive set theory. And the more difficult route is called axiomatic set theory. And naive set theory is the approach that the book takes and most introductory discrete math or math books take. They don't really jump into what the axioms of set theory are. However, this oftentimes leads to a lot of questions from introductory students and maybe a lack of understanding of where things are coming from when we claim certain results about sets. It is sufficient, and it is the approach the book takes. The book doesn't get into axiomatic set theory. However, some of the negative things of naive set theory is that it's a little bit less precise. What I mean by that is that sometimes constructions don't entirely appear evident, doesn't appear evident where they're coming from. And one of the issues here is that we also have the arisal of paradoxes. And the one that we're going to talk about in today's lecture is Russell's paradox. But there are others. Just to define, if you don't know what the word paradox means, the paradox is a self-contradictory statement. So this naive set theory was developed by Cantor, and it was perfectly fine for a very long time. And mathematicians used it to develop ideas. However, the fact remains that these paradoxes still do arise if you're not very, very careful with how you define exactly what a set is and how the set interacts with one another. Different sets interact with one another. So this is fixed by introducing axiomatic set theory. It's a formal logical construction or axiomatic system that we talked about in the last lecture. And most importantly is that there are no paradoxes. So it's a consistent system. For the majority of this course, we will be using naive set theory. I'm not going to formally define or rely on the axioms of set theory too much, but it's important that, at least in this introductory lecture, you understand the differences between these two things, and the fact that what we're doing, even when we do naive set theory, we're kind of implicitly assuming that we've already done the axiomatic set theory to define a consistent logical framework. And regardless, we have that set theory is based around one very simple and powerful proposition. And this is the proposition A, and this is like an epsilon symbol, B, where A and B are two sets. This proposition is the proposition that set A is an element or member of set B. And in this lecture, the goal is going to be to kind of go over certain properties of this, certain things that we can define, and even how to directly define this. And I will briefly touch on the axioms and what their motivation is from axiomatic set theory. But almost immediately, if we have the idea of membership, so something being a member, one set being a member of another set, we can go through and say, define some other propositions as well. This proposition is the proposition that is the negation of A being a member of B, or A is not a member of B. We can define, hopefully define some sort of concept of what's called a subset, which is different, completely different than the membership identity, but it's related to it, membership proposition. If I write B, and then a sideways U here, and a line C, this means B is a subset of C, and this is logically equivalent to the statement for all A in some universal set, or some universe, I should say. This is the universe that B and C are contained in. A, if A is an element of B, then A is an element of C. this is the definition of what a subset is. What it means to be a subset. If A is an element of B, then A is an element of C. And we know from our logical equivalences that this is then, if this is how we were defining what it means to be a subset, is the same thing as saying A is not an element of B, or A is an element of C. Just using our basic logical equivalences that we've talked about before. We can also define what's called being a proper subset. So this idea right here allows for, it's called set equality between the two sets, which will apply a proper subset. Say D is a proper subset of E. This notation right here means D is a proper subset of E this idea right here is the same thing as saying that D is a subset of E and E is not a subset of D. It's saying that there are elements, every element of D is an element of E, but there are elements in E that are not elements of D. So for example, if D is some set of elements A, B, C, and E is some other set of elements A, B, C, D, we would write that D is a proper subset of E because there's D is a subset of E, but E is not a subset of D. So in general, we use the proper subset notation if we know that a set D is a proper subset of E. But if we, in general, if we don't know, we have to assume that it might be a subset. And the reason for this line right here is because we can have a direct idea of set equality. Right? Two sets are equal to one another, or we say that set C is equal to set D in set theory. They contain all the same elements. That's what the most logical way of defining equality would be. But the way that we do this is saying that we use the idea of a subset. We say that if C is a subset of D and D is a subset of E, notice we're not using the proper subset here, but if this is true and this is true, then we say that C is equal to D. So this is typically, if you want to show two sets that are equal to one another, how you would go about proving that. So these are some of the most basic ideas about set interaction. And there are a number of different really good examples in the book. I'll go over some examples right now. But I just want to note, right, that and as kind of like a reminder that the book doesn't go into axiomatic set theory at all. The book just develops naive set theory, and it uses the term object to define a set. A set is a collection of objects without specifying exactly what an object is. This is based on an intuitive notion or idea of an object, which was first stated by Cantor. in 1895. The theory can be directly developed and is developed, and there's really, from a certain standpoint, no reason to go into axiomatic set theory, and this is what many mathematicians thought for a long time. No reason to go into axiomatic set theory, and certainly this is what many mathematicians thought. But if you're not careful with how exactly you define a set, you only use the intuitive definition, certain paradoxes come up. So we'll see these in a little bit. And I want to make a note here. Typically we can write sets using either the roster method or set builder notation. And we'll see some very basic examples in the following the following couple pages. So for the first example, we'll just say talk about the set A, B, C. This is an example of the roster method. Another example be some set, say 0, 1, 2, 3, 4. And it's important for me to note here that the order of elements listed in a set doesn't matter. If I rewrite this as B, A, C, and these two things are the same set. We will later on get into what's called an ordered pair and show that you can actually define an ordered pair as another special type of set that actually the order does matter. But for a fundamental set, the order doesn't matter. The terms in the set might be a collection of ordered terms if written in a certain order, but from the standpoint of just basic set theory, writing down this set is the same thing as writing this set. These two things are the same based on the definition of how we're defining sets. So these two examples that I've written right here are finite sets. Finite set of 3 elements here, finite set of 5 elements right here. And they're both in roster notation, or using the roster method, within which we list out every single one of the elements in the set. So it's a very explicit way of writing down the set. We can also have infinite sets, and we'll see that there are actually different types of infinity. There's what's called countably infinite and uncountably infinite, which is in some sense a larger type of infinity than just the countable infinity. But the most natural first infinite set to start with is the set of natural numbers. This is noted with a double line, n with a double line. And by the end of this lecture, we will actually end up officially constructing this set using formal logic. And this is set of natural numbers is starting at 0. It's 0, 1, 2, 3, 4, all the way up to as high as you want to go and more. It's all of the positive natural numbers, or positive counting numbers. This is also in roster method, with the ellipses here denoting a pattern that should be understood from the first couple terms that are written down. example of a set is the integers. These are 0, positive, negative 1, positive and negative 2, positive and negative 3, and so on and so forth. This is also written down in roster method. We can do things like talk about with the integers now, the set of positive integers. This is set 1, 2, 3, 4, and all positive integers. And again, you can ask, well, this ... here is a little bit ambiguous. But typically, when you see something like that, it means that judging from the pattern of the first couple terms, you can figure out how to extend that pattern. But we'll see that the roster method for infinite sets is not always the nicest way of doing this. However, all of the explicit examples that I've written down so far have used the roster method for writing down the set itself. In this next example, I will give you a direct way of writing down sets using set builder notation. So I write down the set. P in Z such that P is divisible by 2. Equivalently, you could say the set P such that P is in Z and P is divisible by 2. This is an example of set builder notation, or the exposition of a set in terms of saying it's the set of elements in some set, or the set of elements that are in some set and satisfy some predicate. And first, this requires defining what it means to be divisible, which we'll get really into when we start talking about the integers and the integer theory. However, from basic arithmetic, you should hopefully remember what divisible means, and we know that the numbers that are divisible by 2, or the integers that are divisible by 2, are going to be the numbers that we can divide by 2 and get back an integer, and that's going to be 0, plus or minus 2, plus or minus 4, plus or minus 6, and so on and so forth. So this set right here is in roster notation, or this set right here is in roster notation. This set right here is in set builder notation, but it's the same set. So this is important that some sets are easier to write down in a given notation than others. I'm going to use blue, circle of blue, for the roster notation, and I'll use a red circle for anything that's in set builder notation. but so we can specify. So the next step up is the set Q. This is the set of rational numbers and we can write this directly in set builder notation as set of x such that x is equal to p over q, where p is any integer and q is a positive integer. For the collection of all fractions of integers where the denominator has to be non-zero. Hence, we'll take q in z positive. But this is again in set builder notation, where you say q is the set of all x such that x satisfies certain properties. Now, what's surprising is that q is it's called a dense set. We have a very large number of elements in q. However, we can actually show, when we develop the idea of cardinality, that the number of rational numbers is in some sense the same as the number of natural numbers. The two sets have the same cardinality. I know that might sound weird for infinite sets. However, there are infinite sets that are much larger, right, than the natural numbers. And the first big example that you're hopefully familiar with from, say, a calculus course is the set of real numbers, or the real number line. And constructing the set of real numbers is actually relatively complicated, so we're not going to be getting into that. But if you take a course on mathematical analysis, that would be a good thing to look at in that course. But what we will prove in this course that's quite interesting is that the set of real numbers is actually, in some sense, a larger infinite set than the set of rational numbers. Which is very, very neat. By real here, we just mean rational or irrational. But then once we have the set of real numbers, we can go through and we can actually define what's known as the set of complex numbers, which is known as C. And this I can actually write down in set builder notation. We say that set of complex number is all z, such that z is equal to a plus bi, and a and b are both real numbers, and I is something that we call the imaginary unit, or the square root of 1. And there are, again, other ways of constructing the complex numbers that are more rigorous. But for the most part, if you ever take a complex analysis course, this is really all you need to know at the very beginning about what the complex numbers are. But these examples should give you a good example and give you a good beginning point for understanding what we mean when we talk about sets, and specifically subsets, because each one of these sets we can talk about subsets of that set. But what I'm going to switch my attention to right now is more of an example that if we're not careful with our development of set theory, could be a very big problem. And this is called Russell's paradox. You'll notice that when I defined my sets using set builder notation, I was very careful in each example, even in the complex numbers example, to be very specific about what set the thing that I'm defining, or the elements I'm defining, are coming from. Right? And this is very, very important. You always have to say that, talk about where you're pulling elements from, or where you're pulling things from in a given set. And this is an example of a set for which, if you're not careful, you can write down statements in naive set theory that don't make sense in actual axiomatic set theory. So before we do this, to get into this, we'll just talk about the following. We'll consider the set A defined by the following property. For all x, if and only if x is an element of A, if and only if x is not an element of itself. So this statement right here is logically equivalent to a statement that x is an element of A if and only if x is not an element of itself. And we'll see immediately that this gives us a very, very big problem, or a contradiction. And the question here that you want to think about is A a member of itself? Well, let's see. If A is an element of itself, then by definition, by the definition defining property of A, if A is an element of A, then by definition A is not a member of itself. This is one possibility. And the other possibility is if A is not an element of itself, then again, by definition, A is an element of itself. A is a member of itself. And the problem here now is that by the definition of this this A, the defining property of this A, we have a bijection. A is an element of A if and only if A is not an element of A, which is a contradiction. This is the same thing as the statement P if and only if not P, which if you draw the truth table out for, right, we've seen that this is clearly a contradiction. Not P is this, and then P if and only if not P is going to be false and false. So this is, in some sense, a very big problem that we have to resolve, and the resolution is relatively straightforward. The statement A is an element of A is not a valid proposition. In set theory. Specifically, what we'll show is that in the realm of axiomatic set theory, we're going to have axioms in place that actually we can prove using the axioms that statements like having, like this, right, having a set being an element of itself is not possible to have. It's impossible to have. More so, what we'll do is we will also go through and show that this object that we're considering up here is not even a set. Right? This object, or is what's called a class. Right? So if you talk, you can never have, we'll see, what's called a set of all sets. It's not actually a set. So this is why it's really important to specify what sets things are coming from in set theory when you're dealing with things that you're writing down, or propositions that you're writing down. So the set A that Russell created is actually not a set. We'll find out that it's actually impossible to have something that's like this A, or defined like this A. But the main point here is that this paradox that comes about as a result of naive set theory is the reason that we have to be careful in deciding the axioms of set theory. And the last point that I want to make here before starting to get into the what the axioms are is that, you know, a deep discussion of axiomatic set theory could take a one-semester graduate course. We will not be diving into this because we have a lot of other things that we want to do this term. However, we will touch on the axioms in this lecture to give you a basic idea and motivation for why they're important, and also to hopefully give you some more feeling of groundedness, right, when you're thinking about what you're doing with the various mathematical operations. I think that understanding, having a cursory understanding of these axioms really helps you in your knowledge and your understanding. And so to this end, what we're going to do is I'll start right now by giving you a summary of the axioms and one of the things that you want to think about when you're writing down these axioms of set theory. We'll start with a very important idea. And the idea here is that axiomatic set theory is a formalization of what the element of relation must obey. To be a consistent logical system. If we write down that x is an element of y, first and foremost, this must be a valid proposition. For all x and for all y, for all sets x and for all sets y. Which means x is an element of y must be either true or false. It's an exclusive or. So for all sets x, for all sets y, either x is an element of y is true, exclusive or the negation of this is true. So either set x is an element of y or x is not an element of y. In total we have 9 axioms in what's called ZFC set theory. The first 8 of which is known as ZF set theory. Stands for Zermelo-Fraenkel set theory with the axiom of choice. That's the 9th axiom in ZFC set theory. First and foremost, we have 3 basic existence and construction axioms, which assert the existence of certain sets, show us how to define set equality, and we also have one axiom of foundation or regularity, which excludes certain constructions from being sets. This is the we have the existence axiom, the existence of the empty set, which is typically denoted as a circle with a line through it, or just empty brackets. We have the axiom of extensionality, which defines set equality. Then we have the axiom of foundation, or regularity. Which excludes certain objects from being sets. And this is one of the axioms that deals with Russell's paradox. We have 4 basic construction algorithms, or axioms. Which establish rules for building new sets from given sets, these are what's called the parasite axiom, this says given two sets A and B, the set containing A and B is a set. We have the union set axiom to allow us to take the union of sets. The union is an operation that we'll get into a little bit later. We have the replacement axiom, and this is sometimes called separation or restricted comprehension. This axiom helps us avoid Russell's paradox and allows us to use what we talked about before, the set builder notation. And then lastly we have what's called the power set. Axiom, which allows us for any set we can form what's called the power set, or the set of all subsets of the set A. And then the last two axioms are further existence construction axioms, that are newer and more advanced than the others. The first of these is the axiom of infinity, which allows the use of induction to create infinitely sized sets. And the axiom of choice. Which is slightly more advanced than all the other axioms and takes a little bit to really understand what it's saying, but this turns out to be a fundamental axiom to most big theorems in modern mathematics. This is also sometimes called the it's a different principle, but it's equivalent to the what's called the well-order principle. And this is something that's very, very important in modern mathematics. Really, the axiom of choice and everything that is mathematically equivalent to the axiom of choice is very, very important to all of modern mathematics. But if you take the first 8 axioms, you have ZF set theory, and if you take all 9 axioms, you have ZFC set theory, which is ZFC theory, set theory, is the basis for pretty much every modern theorem in modern mathematics and modern mathematical constructions.